Let me give you another algebraic interpretation of principal components, and eventually this will just get us to our formulas. Here we have our point P, and let's suppose we have some origin. If we want to minimize the square of the distance from the point to a line, we want to find the line that minimizes that square. Well, you remember Pythagorean's theorem? Of course you do, right? It's that the sum of the squares of the two legs of a right triangle are equal to the square of the hypotenuse. If we want to minimize the square distance of the point to that line, it's the same thing as maximizing the projection of that point on the line. That's what this value is here, right? X transpose P. X is some unit vector through the origin, and if we project P onto it, that's going to be the vector, and you want to maximize that length. So minimizing the sum of the squares of the distance to the line is the same thing as maximizing the sum of the squares of the projections on that line. A way of writing that is we want to sum up all the squares, and this is just a little bit of a matrix manipulation trick, right? If I wrote my points down here, right, of x1, y1, or an x2, y2, and if this was my line, so maybe it's AB, right? If I multiply x transpose b transpose, so now this is b, xy, xy, bx, all right? If you multiply that all through, what you'll realize is it's exactly that value, okay? It's the sum over all the points of that square of the magnitude, all right? So what that means is algebraically, this maximizing the projected distance can be written like this, right? So our goal is to maximize x transpose bx, but we've got a constraint, right? X is a unit vector. So that means that x transpose x has to equal 1. So what we have to do is we have to maximize this subject to a constraint. All right, so that's what this says here, and I wrote it as m, maximize equal to x transpose mx, where m is b transpose b, so we just have a single matrix. Now, I'm not going to tell you a lot about this method, but I am going to introduce this quick notion of what's called Lagrange multipliers. Here is E, and here's E prime. And you notice that what we added to E prime is this term, lambda times 1 minus x transpose x. So Megan, if everything is solved correctly, 1 minus x transpose x should be what?
0?
Whoa! Yes, 0. So when this thing is solved correctly, it doesn't matter what this lambda is, right? Because it will add 0 to the term. That, in a very hand-wavy way, that is the method of Lagrange multipliers. It says, I'm going to put in a term multiplied by a lambda that will be 0 at the correct solution, and then you solve everything and you've satisfied your Lagrange multiplier method. It turns out in our case it's even easier. So that's our E prime. So what we do now is we take the derivative of that new error function, E prime, with respect to x, and we get this, 2mx plus 2 lambda x is the derivative. And now, in order to minimize this, we set this equal to what, Megan?
0.
0, very good. We actually rehearsed that one this time. And so when you do that, you get this very simple equation that says mx equals lambda x, all right? Forget the positive or negative, it doesn't matter because lambda can go in either direction, all right? So that's a very special x, right? So when I multiply x by a matrix M, if I get back a linear multiplier, in this case lambda, of x, that means x is an eigenvector of the matrix M. So that means that x is going to be an eigenvector of this b transpose b. All right? So this axis of least inertia, this solution where we minimize the distance to the axes, the sum of the square distances, which is the same as maximizing the distance along, says it has something to do with this matrix b transpose b, where b was that list of all those points.